Welcome back to Decentralized Application Development Crashcasts. I'm Sheila, and before we dive into today's exciting topic, I want to remind our amazing listeners that your support means the world to us. If you're enjoying the show, please take a moment to rate us on your favorite podcast platform. It really helps us reach more developers like you.
And I'm Victor, ready to explore the fascinating world of distributed hash tables with you all. Today, we're continuing our journey through Chapter 3, focusing on the Chord algorithm, a key player in the DHT world.
That's right, Victor. And to kick things off, I have a brain teaser for our listeners. Here's the quiz question. In a Chord network with 2 LM nodes, what's the maximum number of steps required to resolve a lookup query?
Ooh, that's a great question, Sheila. It really gets to the heart of Chord's efficiency. Listeners, take a moment to think about it. Consider how Chord organizes its network and how information is passed between nodes. We'll reveal the answer at the end of the episode, so stay tuned.
Now, before we dive deeper, let's quickly recap some key terms. Victor, could you remind our listeners what a DHT is and its basic operations?
Certainly. A distributed hash table, or DHT, is a decentralized system for storing and retrieving data. It uses a key-value pair model, where each piece of data is associated with a unique key. The 2 main operations are put, which stores data in the network, and get, which retrieves data using its key. DHTs distribute this data across multiple nodes in a network, ensuring no single point of failure.
Thanks, Victor. Now let's focus on the Chord algorithm. Can you give us a brief introduction to what Chord is and why it was developed?
Of course. Chord is a protocol and algorithm designed for efficiently locating nodes that store particular data items in a peer-to-peer distributed system. It was developed in 2001 by researchers at MIT and Berkeley to address scalability issues in peer-to-peer systems. The key innovation of Chord is its use of consistent hashing to assign keys to nodes, which helps balance the load and allows for efficient routing.
Interesting. So, how does Chord organize its network? I've heard something about a ring structure.
You're right, Sheila. Chord organizes its nodes into a virtual ring. Imagine a clock face. That's a great analogy for understanding Chord's structure. Each node in the network is assigned a position on this clock based on its identifier, which is typically a hash of its IP address. The keys of data items are also hashed to determine their position on this ring.
That's a helpful analogy, Victor. So, if I understand correctly, both nodes and data keys share the same clock face. How does this help in locating data?
Exactly. This shared space is what makes Chord efficient. When you want to find a piece of data, you look for the node that's clockwise from the key's position. This node is responsible for storing that data or knowing where it's stored. It's like saying, I'm looking for key 42, so I'll ask the node at position 45 because it's the first one clockwise from 42.
That makes sense. But with potentially millions of nodes, wouldn't it take a long time to go around the entire ring to find the right node?
Great question, Sheila. This is where Chord's brilliance really shines. Instead of each node only knowing about its immediate successor, Chord uses what's called a finger table. This is like a shortcut system that allows nodes to skip large portions of the ring.
A finger table? That sounds intriguing. How does it work?
Think of it as a logarithmic shortcut system. Each node maintains a finger table with up to m entries, where 2m is the size of the identifier space. The ith entry in the table points to the first node that succeeds the current node by at least 2 prans I1 positions on the ring. This means a node can quickly jump to distant parts of the ring, drastically reducing the number of hops needed to find data.
Wow, that's clever. So it's like having a mix of short-distance and long-distance connections, allowing for quick navigation around the ring.
Exactly. This is what gives Chord its efficiency. In fact, this relates to our quiz question. With this finger table system, Chord can resolve any lookup query in at most O log n steps, where n is the number of nodes in the network. This logarithmic scaling is a key advantage of Chord over other DHT algorithms.
That's impressive. But what happens when nodes join or leave the network? Doesn't that disrupt the whole system?
Another excellent question. Chord is designed to handle dynamic membership efficiently. When a new node joins, it only needs to contact a few existing nodes to initialize its finger table and transfer the appropriate keys. Similarly, when a node leaves, only a small number of nodes need to update their finger tables and take over the departing node's keys. This process ensures that the network remains stable and efficient, even as nodes come and go.
I see. Are there any real-world implementations of Chord that our listeners might be familiar with?
Absolutely. While Chord itself isn't as widely used in its pure form today, its principles have influenced many modern distributed systems. For example, Amazon's Dynamo database, which powers services like Amazon's shopping cart, uses concepts similar to Chord for distributing data across nodes. Additionally, some peer-to-peer file-sharing systems have incorporated Chord-like algorithms for efficient file location.
That's fascinating. How does Chord compare to other DHT algorithms we've mentioned, like Kademlia?
Great question for comparison. While both Chord and Kademlia are DHT algorithms, they have some key differences. Kademlia uses a tree-like structure instead of a ring, and its routing table is somewhat more flexible than Chord's finger table. Kademlia also uses a different distance metric for routing. In practice, Kademlia has become more popular in some applications, particularly in decentralized networks like BitTorrent, due to its resistance to certain network attacks. However, Chord's simplicity and provable performance guarantees make it an important algorithm to study and understand.
Thank you, Victor. That really helps put Chord in context. Now, before we wrap up, let's reveal the answer to our quiz question. In a Chord network with 200 nodes, what's the maximum number of steps required to resolve a lookup query?
Ah yes, the big reveal. The answer is m steps. This comes directly from Chord's logarithmic efficiency. Since there are 2 aulatas nodes and each step in the lookup process halves the distance to the target, it takes at most m steps to reach any key in the network. This is equivalent to O log n, where n is the number of nodes.
Excellent. To summarize today's episode, we've learned about the Chord algorithm, a key player in distributed hash tables. We covered its ring structure, the innovative use of finger tables for efficient routing, and how it handles nodes joining and leaving the network. We also touched on its real-world applications and how it compares to other DHT algorithms.
That's a great summary, Sheila. I hope our listeners found this deep dive into Chord as fascinating as we did. Remember, understanding these fundamental algorithms is crucial for anyone looking to work with or develop decentralized applications.
Absolutely, Victor. And to our wonderful listeners, thank you for joining us on this journey through the world of decentralized systems. If you enjoyed today's episode, please visit crashcasts.com to find more resources and join our vibrant Discord community. Your support on Patreon helps us keep producing high-quality content. Don't forget to subscribe and rate our podcast. It really does make a difference. Until next time, keep exploring the decentralized world.